Hi everybody, welcome back to one more session on biomolecules, and today we will be continuing with carbohydrates. The topic of today is mainly to discuss the isomerism, specifically speaking the stereoisomerism which has been found within the carbohydrates. If we go to consider isomerism or isomers are those molecules which are having the same molecular formula but they differ in the structural formulas. Now this could be of two types, the structural isomers as well as the stereoisomers. Now what do you mean by structural isomerism and what do you mean by stereoisomerism? Structural isomers, they have the same molecular formula, but they have different structures. And coming to stereoisomers, they mainly differ mainly on the spatial configuration of the various moieties which have been attached to the different carbon atoms or the different atoms which have been involved in the formation. So if you go to consider isomerism, you can divide it into structural isomerism or the stereoisomerism. Structural isomerism is again divided into chain isomerism, positional isomerism, functional isomerism, metamerism, tautomerism, as well as ring chain isomerism, which I will not be dealing right now in this particular session. This session is mainly concentrating on the stereoisomerism, and we would be talking mainly the stereoisomerism of carbohydrates. Now, stereoisomerism of carbohydrates can be divided into two types. One is the geometrical isomerism and the second one is the optical isomerism. Now, what is that? How it has been found to be different to each other. Geometrical isomerism, it mainly occurs when there occurs a difference in the spatial arrangement across a double bond. That is, in carbohydrates, if you have two molecules which are being found to be attached by a double bond, and if there occurs difference in the spatial arrangement across these carbon-carbon double bonds, then you call them as geometrical isomers or geometrical isomers. Now, considering the optical isomers. The optical isomers, they are isomers which differ in the arrangement of atoms in 3D space, which will create mirror images of each other. Now, let me just show you a depiction of this. If you go to have a Okay, now let's consider the optical isomers. If you have two different isomers which are having the same molecular formula, but the 3D arrangement of the different moieties in the space or the spatial arrangement, if they differ in the spatial arrangement, you can see this over here. The white and the yellow is being found towards one particular location over here, and it is being found in the opposite direction for the other. So in such cases, they are referred to as the optical isomers. And in the case of geometrical isomers, there are two carbon atoms which are here and they are being linked together by double bonds. And across this carbon-carbon double bond moieties, there are two different spatial arrangements. That is, two greens are over here in one side, and in this form the greens are in opposite sides, or the whites are in the same side or the whites are in the opposite side. So this is a general depiction of stereoisomers, especially geometrical isomers and optical isomers. Now we are going into the details of it in the coming session. Let's go into that. First, let's start with optical isomers. Before I need to discuss the concept of optical isomers, I need to introduce you to with a chiral or a asymmetric carbon. What is that? The three-dimensional arrangement of the atoms around the carbon are such that if four different groups are attached to it, they can be arranged in two different ways. Now just look into this case. Now what is a chiral or a asymmetric moiety? A carbon atom to which four different atoms or groups of atoms are attached, that is said to be asymmetric or chiral in nature. Now, if you go to look into this glucose moiety, you can see that the C2 carbon, okay, that has 4 different groups attached to it. One is the CHO, second one is H, OH, and of course this moiety altogether. So the C2 carbon of glucose is being found to be asymmetric or chiral in nature. Now the same way you also have C2, C3, C4 and C5. There are 4 asymmetric carbon atoms when we go to consider the glucose moiety. Now let's look another example over here, glyceraldehyde. If you go to consider glyceraldehyde, okay, uh, you have the second carbon atom, okay. In glyceraldehyde, it is having C2. C2 is being found to be as a asymmetric carbon atom. And you can see that here CHO is being found attached, H is attached, OH is attached, and this is being found to be attached. So the C2 moiety is being found to be asymmetric in glyceraldehyde. But if you go to consider the C3 moiety, you can see that it is attached to H and H, which are both being found to be. So C3 is not being found to be asymmetric. So when you go to consider asymmetric or chiral moieties, you can see that the moieties which are being attached to that could be arranged in 2 different orientations. That is, now when I go to consider the C2 carbon atom over here, the moieties which are being attached to it other than the carbonyl and the penultimate carbon atom, you can see that the other moieties which are being found to attach to it, they could be what in 2 different locations. Now for orientations, that's what. In this case, H and OH, the OH is being found towards the right side in one moiety of glyceraldehyde, and in the second moiety you can see that it is being found towards the opposite or towards the left. The hydroxyl group is being found towards the right. So on the basis of this, and you can see these two, now glyceraldehyde and glyceraldehyde, it's just the same glyceraldehyde which I had showed, but they are only differing in the location of the hydroxyl group. If hydroxyl group is being found towards the right, you call it as a D form or the dextro form, and if it is being found towards the left, you call it as the L form or the lever form over here. And this can be either written as D and the L form also. Now, if you go to consider these two moieties, now for example, D-glyceraldehyde and L-glyceraldehyde, you can see that they differ from each other only in the disposition of various atoms or groups in the space surrounding the carbon atom, asymmetric carbon atom. Which is the asymmetric carbon atom? In the C2. They differ from each other only in the orientation of the moieties associated with the asymmetric carbon atom. And these two moieties are also being found to be what? Mirror images of each other, and they are not also being found to be not superimposable to each other. So in such cases, the molecules which are mirror images of each other and which differ in the atoms or groups only in the space around the asymmetric carbon atom and which are not superimposable or non-identical with each other, non-identical superimages, in such cases they are considered to be as optical isomers or the enantiomers. I think it's clear to you. You just look, they are differing with each other only at the moieties across the asymmetric carbon atom, and they are mirror images of each other, but they are not superimposable with each other also. If these three conditions are being considered, then that isomers are considered to be as enantiomers or the optical isomers. And we can see that usually if you have a n number of asymmetric carbon atoms, according to the Ley-Bell-Van 't Hoff rule, the total number of optical isomers or stereoisomers of that particular compound will be 2 raised to n. Now, in this case, you can see how many asymmetric carbon atoms are there. It is having only one asymmetric carbon. So, 2 raised to 3. That number of optical isomers or enantiomers are only being possible for glyceraldehyde. Now let's take the next example of glucose. In the case of glucose, you can see that here. Now, let me just consider. Now, in this case, you are having what? In glucose, you have more than one asymmetric carbon atom. In such case, the D and the L form is being notated basically based upon the hydroxyl group attached to the penultimate carbon. Okay, penultimate is a here. In this case, there are 6 carbon atoms. So the orientation of the hydroxyl group at the penultimate carbon atom or the C5 carbon atom is being noted. And you can see that in D-glucose, the hydroxyl group is found towards the right, and hence this is D-glucose. And here in the penultimate carbon atom, the hydroxyl moiety is found towards the left, and hence we call it as a L-glucose. So in the D and the L isomers, you check the orientation of the hydroxyl group of the penultimate carbon atom. The same was the case with glyceraldehyde also. You can see we are checking the penultimate, or if there are 3, the second carbon atom was being checked. So such a thing is also, now let's just look into what it is also applicable for the ketoses also. We'll just look into what are the ketoses. Now, considering the asymmetric carbon atoms in the ketoses. Okay. If you go to take the ketose, now ketose is, fructose is an example for ketose. You can see that the number of asymmetric carbon atom over here, it has been found to be lesser than that of the, now glucose is a what? Glucose is a aldohexose, or it is a aldehyde group, and both of them are having 6 carbon atoms. But in the case of ketoses, they usually have one less asymmetric carbon atom compared to that of the aldose. Now, in the case of glyceraldehyde, okay, glyceraldehyde, it is having a asymmetric carbon atom, but its counterpart dihydroxyacetone will not have, does not have a asymmetric carbon atom, so it is not having the property of optical isomers. But all the other ketoses which we have do have a asymmetric carbon atom, and uh, what asymmetric carbon atom, and they do exhibit the property of optical isomers. So now let's consider another case of isomers, considering both the aldehydes as well as the ketoses. Now if you go to consider an aldehyde and a keto isomer, you can consider it as an aldo-keto isomerism. Now what is that? Why is it that so? When you go to structurally analyze these two components, now that is if a 6 carbon aldose aldehyde and a 6 carbon ketose, you can see that the difference mainly happens at the position of the C double bond O group. If the C double bond O group is being found to be terminal, then it is considered to be as an aldohexose. And if it is being found to be subterminal or at another position, then we consider it to be as a ketose sugar. So this is a case of functional isomerism which has been happening between, that is, the functional group here becomes aldehyde when the C double bond O is being found terminal, and the C double bond O becomes a keto group or a ketone group when it becomes a keto sugar. So this is the case of aldo-keto isomerism, which is being found, is another case of stereoisomerism also, which is being found in the carbohydrates. So we came across the first one, the occurrence of asymmetric or chiral atoms, and that could contribute to what? Optical isomers or enantiomers, which are nothing but difference in the disposition of various atoms around the asymmetric carbon atom, which are being found to be mirror images of each other and which are not superimposable. And we could we also spoke about the aldo-keto isomers, which are differences or stereoisomerism which could be found between the aldo sugar groups as well as the keto sugars. Then now let's move on to the next one of next type of stereoisomerism which have been found in carbohydrates. The next one is a case called diastereoisomers. Now, what do you mean by diastereoisomers? These are stereoisomers which are not mirror images to one another. Now, before going into that, let me just tell you, if you go to consider the number of asymmetric carbon atoms, not always there will be one asymmetric carbon atom between two different molecules. There might be different asymmetric carbon atoms. And if the spatial orientation is being found to be different at different uh, more than one, if it has been different in more than one chiral centers, and then which develop a pair of isomers which are not mirror images of each other, then we call them as diastereoisomers. Let me just repeat it to you here, taking this example of D mannose and D galactose. If you go to consider these two moieties, you can see that this is the first carbon atom, second carbon atom. In this, the C2 is being found to be a what? Asymmetric carbon atom. And do identify the orientation of the moieties H and OH, which is being attached to the asymmetric carbon. You can see that OH is being found towards one place, okay, and it is being found to be at another location in the case of this. So in this particular case, what happens? They are differing in the hydroxyl group orientation on either side. Then if you go into the next one, okay, they are having the same. They are having the same what orientation OH and H. And if you are going to consider the third carbon atom, not third, the fourth carbon atom. The fourth carbon atom, you can see that again their orientation is being found to be different. So, in the C2 chiral center as well as in the what 2, this is 2, 3 and the 4. 2 and the 4, they are being found to be, they have a different orientation across the chiral center. And if you go to look at each other, they are not mirror images of each other also. Okay, because they are oriented different only at two chiral centers, and they are not mirror images of each other also. In such cases, these isomers are called the diastereoisomers, and such isomers which are not mirror images of each other and which are not superimposable on one another are called the diastereoisomers. So consider your case when the moieties attached to more than one chiral centers are being found to be different, and when they are not mirror images of each other, you call those isomers as diastereoisomers. Now do notice over here, it is D mannose and D galactose, and the D is given for the orientation of the hydroxyl group at the penultimate carbon atom. You can see the penultimate carbon atom here, DOH is being found towards the right. Same in the case of D galactose also, D mannose and D galactose. So this is also a case of stereoisomerism or difference in the spatial arrangement of different moieties which are being found in the carbohydrates. Now let's move on to the next type of stereoisomerism which we can find in carbohydrates. If you go to consider the moieties over here, I have three different components: D galactose, it's spelled wrong, D glucose and D mannose. If you go to consider D glucose and D mannose, just take these two. You can see that they are the same at the C1 carbon atom, but at the C2 carbon atom or the asymmetric carbon atom C2, you can see that they are different. They have different orientations. At C3, they have the same. At C4, they have the same orientation. C5, they have the same orientation. C6 also they have. So D glucose and D mannose, they are what? They are differing in the configuration around one carbon atom other than the carbonyl carbon atom and the penultimate carbon. This is the carbonyl carbon atom and this is the penultimate carbon atom. Other than these two, they are differing only in one carbon atom. Now go to consider D galactose and D glucose. You have the carbonyl atom here. Go to consider C2, they both are same. C3, they both are same. C4, you can see the orientation of hydroxyl group and OH is being found to be different. And then C5, they have H and OH, that's different. And CH2OH, they are being found to be the same. So they are D-galactose and D-glucose is being found to be differing from each other only at the C4 asymmetric carbon atom. Such isomers which differ in the configuration around one carbon atom other than the carbonyl carbon and the penultimate carbon are referred to as the epimers. And glucose and galactose, which are having the same structural formula but differ only in the position of the hydroxyl group at C4, they are considered to be as epimers. And D-glucose and D-mannose, they are another example of epimers because they differ only at the hydroxyl group orientation at the C2 position. So considering all these what you came across right now, we have enantiomers. Okay, enantiomers are which are mirror images of each other, and the diastereomers, these are the ones which are having what they are they have an opposite configuration and at one or more chiral centers, but they are not mirror images. And we have finally the epimers, which are two sugars which differ in the configuration at only one chiral center. Here in enantiomers, they are mirror images. In diastereomers, they are differing in the orientation at more than one chiral center, and hence they are not mirror images of each other. And in epimers, they are differing in the configuration at only at one chiral center. So that is, these are some of the cases of stereochemistry which occurs in the carbohydrates. Now, when we go to consider the carbohydrates, of course, we also have discussed the anomers. What are anomers? I have mentioned earlier, when glucose is being present in solution, it can form cyclized structures called hemiacetyl forms. And sometimes you can see that the hydroxyl group, which is being attached to the anomeric carbon, okay, that would be found to be different, okay, which is the hydroxyl group around the carbonyl carbon atom in the cyclic structure could be different in orientation when we consider the cyclic structure, and based upon that they are being called as alpha or the beta configurations. The alpha form, in the alpha form what happens, the hydroxyl group is attached to the carbon atom is on the right side, okay. Now this is towards the, this is a carbonyl carbon atom and it has been found to be attached to the hydroxyl group has been found attached to the right side, and that is called the alpha form. And when this is a carbonyl atom and when it is being attached to the left side, it is being considered to be as a beta form. So monomers that differ in the configuration of moieties, of hydroxyl moieties, which are only around the carbonyl carbon, that is called the cyclic, in the cyclic structure, they are called as to be as anomers. This we have already discussed, and in solution, of course, alpha form and beta form will undergo, will occur together in equilibrium, and they can easily convert with each other, as we had already discussed earlier. Now, let's talk about the geometrical isomerism. Hope so you remember we divided our stereoisomerism into optical isomerism and geometrical isomerism at the beginning. Now, what is geometrical isomerism? On either side of a double bond, if the radicals are being found to be on the same side, then you call them as cis form. And if they are being found on the opposite side, then you call it as trans. Now, just have a look at this. COOH and COOH, they are on the same side. And hydrogen in malic acid, they are being found on the same side. That is called the cis form. But in the trans form, COOH and COOH, they are on opposite sides of the, when you consider the double bonded carbon atoms, the radicals, the like radicals are being found on the opposite side, and here hydrogen are also being found to be on the opposite side. So this is called the trans form and this is called the cis form. So these are also two types of geometrical isomers which are being found in carbohydrates, and some of these properties other than these stereoisomeric properties, you can see that various other properties are also being contributed to the carbohydrates because of its stereoisomerism. And one such is the optical activity. What is the optical activity? Of course, you know that what is an asymmetric carbon atom. And we had spoken about the asymmetric carbon atom and the optical or the enantiomers. Optical isomers or the enantiomers. So when you have a compound which is having an asymmetric carbon atom, and when you pass through it a plain polarized light, that is, you have a substance, a solution, which is a carbohydrate which is having an asymmetric carbon atom. It is dissolved in a solution, and if I pass through it, now for example I can show it over here. If this is a solution which is of carbohydrate, and it is also having an asymmetric carbon atom, and if I pass through it a plain polarized light, and if it moves the plain polarized light towards the right or the left, if it is causing a change in the plane, the rotation, that is, if it is changing the plane polarized light either towards one side, to either to the right or the left, then that means that particular substance is being found to be optically active. If the substance is being moved towards the right or in the clockwise direction, it is considered to be as what is rotated? The plane polarized light. If it is being moved towards the right or the clockwise, then that substance is considered to be as dextrorotatory. And if the substance moves it towards the left or in the anti-clockwise, it moves a plane polarized light into the left or in the anti-clockwise direction, it is called the levorotatory. So this is another property of carbohydrates, that is, if they become optically active and they are able, they will be asymmetric, they will have asymmetric carbon atoms, and if they move the plane polarized light either to the left or the right, you call them as dextrorotatory or levorotatory in nature. And every carbohydrate or every molecule has a specific angle of rotation. Now it does not move it at a particular, like all does not move it at a specific at the same angle. Now if you go to consider glucose, glucose changes the plane polarized light to at a degree of about 52.5 degrees, and fructose, if the solution which you use through which you pass the plane polarized light is fructose, it will move the plane polarized light in the levo direction or towards the left at an angle of about minus 91. Minus, or it is at the left, it will move it to 91 degrees. So you can, this property can be used to find out what is a carbohydrate which we have. Now, as a continuation of this, let me just tell you about a racemic mixture. Now, what is a racemic mixture? Now, if a component is having, or if you consider a racemic, if you take a particular component and consider that contains D as well as L forms in the equal proportion, then it will not have optical activity. So let me just explain it to you in a different point of view. If I go to take some alpha D glucose containing sugar, okay, I'm taking a freshly prepared alpha D glucose containing solution, and then what happened? Then that glucose will have a specific rotation of about, and I pass a plain polarized light to it. It will have a specific angle of rotation called 112 degree. Then this will gradually decrease and it will become stable to about 52.5 degree. Now, if I take another freshly prepared solution of beta D glucose, you can see that it will have a specific rotation of plus 19 degree, and then it will further increase and to become 52.5 degree. So what happens to it? Though I take freshly prepared solution of these sugars, let it be aldehyde or ketone group, if you take them, you can see that a change in the specific rotation of the that is when they are dissolved in solids, in solutions, what happens? A change in the specific rotation of or plain polarized light happens and it becomes to an equilibrium. And this change is referred to as mutarotation. And what is happening over here? When mutarotation happens, what happens? The mixture becomes in such a way that it will contain equal quantity of both the isomers D and the L isomers. When it is having a alpha D glucose, that is a alpha D glucose, okay, that is, you can see over here, it is a this is a alpha D glucose and this is a beta D glucose. So when it is being shifting from the alpha to the beta form, okay, what happens is this change of specific rotation will happen until it becomes in the equilibrium stage. So a shift is mainly been happening, and in a racemic mixture which will contain equal amount of the DL isomers as well as the alpha form and the beta form, that is referred to as the racemic mixture. So these are some of the properties of monosaccharides which we have discussed. Hope so it is clear to you. Thank you for now.